So I think you're the perfect audience for what I want to sort of disseminate. So we had some different backgrounds here. So I think this is a good talk for what I sort of have in mind is a good talk for this audience, but feel free to interject if you want to take it a different direction, because this is something that can be looked at purely algebraically, purely analytically, purely differential geometrically, or computationally. And I'm sort of leaning more and more towards the computational side. But in fact, that's why I want to get more ideas out there, because I need people who really know things like Macaulay and other tools to like grab onto this and start playing with the ideals. So I'm interested in basically three general questions. These are absurdly general, but let me just sort of use them to set the scene. Okay, so the first question is, can we detect any sort of order in the zoo, in say the jungle of differential PDEs? Does anyone know that reference of calling PDEs a jungle? This is a
No.
It's an Andre Vey commented about actually relating to L.A. Cartani. So there's this impenetrable jungle a nearly impenetrable jungle when you look at differential systems. So and these pseudogroups. So is there any sort of order in this jungle? Is it just are PDEs just wild, or can we actually understand how they behave and how they relate to one another? Two, can we identify in advance whether we can solve a given PDE using our favorite techniques? I'll say what I mean by favorite techniques. These are my favorite techniques, not necessarily your favorite techniques. And three, so if someone hands me a PDE, I want to be able to answer, can I solve it or not without doing any actual solving, right? Sort of a predictive statement. And second, can we generate or maybe parameterize those PDEs that you can solve using our favorite techniques? So those are the three questions that are sort of always in the back of my mind, right? And so the sort of structure I want to talk about today is based on these. Before I get into that, let me introduce what I call the favorite techniques. This is the idea of involutivity. So this is going to be a loose definition. I'll give a precise one later. In fact, the goal of this talk and the paper this talk is sort of based on is to write down explicitly what this condition is, as opposed to just sort of having a vague notion. So let's say what should we call it? A motivational definition. Let's call it that. Okay, so a PDE, and I haven't even said what I really mean by PDE yet. Hold up there. Right? A PDE is called involutive if it admits analytic families of analytic solutions to analytic initial value problems. so that's the idea. So this definition goes back to so certainly L.A. Cartan in like the 1890s and 1910s. But also earlier, people like Darboux were basically using the same approach. So the idea was, if you're given some system of PDEs and you want to solve a generic initial value problem, so not some sort of boundary value problem, but like what's often called the free Cauchy problem, where you say, for which initial conditions in an open domain can I find a local solution, right? So it's a local free initial value problem, and in many very interesting cases, in fact, I argue almost all of the interesting equations so up in differential geometry, the answer is that you always can, and in fact, you can do even more. You can parameterize the solution set. So you can say exactly, you can parameterize the initial conditions for which you have solutions, and it turns out the parameterization is based on analytic functions. So for a given choice, an analytic choice of analytic functions, you can make analytic solutions, and it's a really great situation. So when this happens, that's sort of what the word involutive is. It's been more and more refined over the years.
And so this is for one single?
This is for a system of PDEs.
System.
And it doesn't care about, it's not a question of order or degree or number of variables. It's a very generic sort of statement. In fact, we'll see this is actually a property of differential ideals. So actually a purely algebraic concept, actually, which is really the amazing part about it. Okay, so in order to sort of set up the general statement and have it make sense, maybe I'll go to this tiny little board and do 3 small examples. So these will just leave it over here.
I thought I told you.
No, I'll use the board.
Oh, you want to use the board?
I'll use the board and then I'll lower this at the end. Yeah, so let's just consider a situation that we all know, right? So I'll just do 3 really simple examples that everyone has seen, I'm sure, before in one form or another. So let's consider a function u of x1, x2. And being a geometer, I put my indices up, right? And let's consider 3 different PDEs. We've got u22 equals u11. We've got u22 equals minus u11. And we've got u22 equals 0. These are our sort of favorite second order PDEs in 2 variables. So the way someone like me looks at this, and I'm guessing some of you also, if your background is sort of differential algebra, is you don't really like thinking about partial derivatives. You like thinking about formal exterior derivatives and these sort of purely algebraic concepts. You don't want to deal with individual coordinates. So what we do, or one way to do this, is to work on, let's make a manifold M, which is J2R2R, so that's second order jet space, which is essentially the same thing as, what is it? That's a count, I think it's R8. So this is going to be a space with local coordinates x1, x2, let's call it U, P1, P2, U11, U12, U22. So 1, 2, 3, 4, 5, 6, 7, 8. Yeah, okay. So we've got essentially R8 with these local coordinates. And we're going to express the fact that we're talking about a second order differential equation by writing down what's called the contact system. So we've got, I'll write it as 3 different one forms. So theta 0 is du minus p1 dx1 minus p2 dx2. Theta 1 is dp1 minus u11 dx1 minus u12 dx2. And theta 3 is the next one. Theta 2 is dp2. So these 2 are the same because I'm sort of implicitly assuming the second derivatives commute. Right? So we're working in u12 is u21 already. You could impose that in the next level, but it's sort of not worth doing that extra step. So this is a system of, so these are 3 one forms. So where do these live? Well, these 3 things, each of these is in, actually their span, right? Their span is sitting in T star M. So if you think of this as being, this is maybe a C infinity M module. Right, so look at the dual space and the tangent space. That's where differential forms live. I've got 3 different forms that are independent by the way they're written. These are all the D's of all of these would be independent. The independent basis of the basis of T star M at a point. So I've got these 3 independent one forms in T star M, and I take their span. I get a 3-dimensional subspace. And in fact, this is more than just a module, right? This is actually one layer of the entire exterior algebra. So if you keep wedging forms, you get the entire exterior algebra, which is often written, so these form an ideal in, you often write it omega m, depending, or I usually write it this way because I like using omega for other things, so let me move this up.
Okay, yeah, that's all right.
So I usually write big wedge T star m, right? So it's the, often people just write it this way. So it's the, right, so this is the...
So you mean they generate?
Yeah, they generate an ideal. In fact, I want to do even more. I want to say they generate a differential ideal. So let's say that these things generate I. So by span, I mean span in the sense of ideals. And I want to impose the condition that di is contained in I. so that if you take the exterior derivative, everything is still in the ideal. That's a slightly stronger statement than what I have so far, which is the algebraic ideal. I want to be able to differentiate these. So in order to understand that algebraically, I'm going to put in three more generators. And let me sort of squeeze this in here. So I'm going to put in some more things. I'm just going to put in the derivatives of these three. Because if I put in their derivatives, then obviously it's going to be closed under differentiation, assuming because d squared is 0, right? That's the whole point of d. So if I put in their first derivatives, and then it's all wrapped up in d of I is contained in I. So I've got d theta 0 is ddu is 0, so it's minus dp1 wedge dx1 minus dp2 wedge dx2. D theta 1 is minus u1, minus du11 wedge dx1 minus d, if I get it right, du12 wedge dx2, and d theta 2 is minus du12 wedge dx1 minus du22 dx2. And you can see that all of these, if you differentiate again, you get 0, of course. They're all closed. Yeah, so that's sort of this is an ideal we might consider. This is the contact ideal on J2R2R. Now, I've written this in coordinates. For those of you who are more sort of algebraically inclined, this is actually completely canonical. So this actually is a coordinate choice on this manifold, which you can construct these forms in a purely algebraic way by looking at the Hilbert form on the Grassmannian. So actually, this is so if you ever think about like the university bundle over a Grassmannian, so you have a plane sitting in some space. You could at each point on the plane you look at the plane or the line through that point in the plane, right? This is a sort of universal bundle over the Grassmannian, and if you coordinatize all that and project onto any sort of any non-trivial direction, you get this system. So even though this looks like a coordinate choice, it's really not. It's just simply it's actually a purely sort of categorical ideal. All right, so that's sort of beside the point, though. So the thing I was actually trying to do is get back to these three statements here. So this so far doesn't include those. Notice that the interesting part of this ideal is really the derivative part, because when I impose either of these three conditions, that's setting a condition, say, on U22. So I'm deciding what I want this term to be, and that says what this term should be. Now these three terms, these are all just independent one forms. The question is what happens when I differentiate them when the ideal includes the second derivatives. So each of these three examples leads me to one of three different matrix systems. I'm going to leave off theta 0. One thing you can observe right away is that because of the symmetry here, if I say that I'm already in the ideal and I mod out by theta 0, theta 1, theta 2, so if I say take dp1 equals this and put it in there, and the dx1s and the dx2s are going to cancel because of these two terms are equal. So I actually don't need to worry about this term anymore at all. It's just sort of boring because this is 0 mod theta 0, theta 1, theta 2. Okay, so I have these three interesting systems which look like this. So it's minus du11, du12, du12, du22, wedge dx1, dx2. So this is an equation of two forms, right? Each of these is a one form. In wedging one forms, I have a two form. These are one forms, and their derivative is a two form. So this is what might be called the structural equations of these, of this original differential equations. And the thing we're doing is, we're really, this is always the same, this is always the same. Like, the thing that's interesting is the shape of this matrix. So for each of these three examples, I get three matrices. In fact, I'm going to erase this and move all this up, because I want to leave up the last line for later. So, yeah, I'll just do that. And if you haven't used the contact system, leads to much. It's just, imagine what you're doing is you just keep taking derivatives until you get bored and check all the cross derivatives, and everything cancels except for the last term, and that's what you look at. That's basically the story here. So we have this system that looks like d theta a, this is an index, is pi ai wedge dxi. That's the sort of thing I just wrote down. So again, this index was going, say, 0, 1, 2, and I was going 1, 2, but the first row of this was 0. So I've got three different cases. I've got the pi AI matrix is either of the form, yeah, I guess I'll put that back in, 0, 0, let me just say pi 1, 1, pi 1, 2, pi 1, 2, pi 1, 1, or pi 1, 1, pi 1, 2, pi 1, 2, negative pi 1, 1, or 0, 0, pi 1, 1, pi 1, 2, pi 1, 2, 0. So these are these three matrices of one forms that correspond with these three differential equations. So these are
why is it the 3 by 2?
Oh, I just put the theta 0 back in.
Oh,
So
okay, all right, okay.
Just so my indexing isn't wrong. Yeah.
Okay.
So you can ignore that row. It's totally worthless. Yeah. So I've got these three 2 by 2 matrices, which somehow characterize each of these three equations. And one thing you might do immediately when you look at these is you ask, when are these, say, non-degenerate, right? I just taught linear algebra this semester, so so what are you going to do? Let's take determinants, right? So we've got pi 1, 1, pi 1, 2 minus pi 1, 2, pi 1, 2 equals 0. This one is pi 1, 1. Oh, sorry, that's not right. Right. That's let's see.
So yeah. Are the pi 1, 1 in each matrix the same?
Yes. So in actually each case, this is like du 1, 1.
Okay.
And this is like du 1, 2, and then this is whatever is left over from there. I just want to label it sort of a generic way because it's actually the coordinates it came from actually don't matter. The only thing that ends up mattering is the shape of this matrix. By shape, we're going to talk about subspaces across Mani in a moment, but this is sort of the key. All the information about these PDs is contained in these different matrices of one forms. Okay, so these are the conditions under which these three matrices fail to be rank 2. And we know, of course, that so if you think about, looking at the roots of this, then, well, so this, let's just say this is what we call hyperbolic. This is what we call elliptic. And this is what we call parabolic. Now those words are familiar because when you see these, you immediately think of these are the prototypes for everything we basically do with at least second order PDEs or sometimes first order PDEs. Is we try to separate them into these three different cases, and of course these are all coming from the idea of the characteristics. So we know the characteristic, if you remember from sort of introductory PDE days, or from algebra, right? That an equation like this or like this, right, has two real roots. This has two complex roots, and this has one real root of multiplicity 2. So there's some variety hiding in here, which is, you can see somehow coming out of the rank 1 condition of these matrices that is characterizing how these three differential equations are different. And we're going to try to pinpoint exactly what's going on there. So usually, say, in undergraduate PD class, this is where the story stops. And you say, well, each of these has different characteristics. We can use that to build solutions. And they're just different. Like we've got a Laplace equation, wave equation, and heat equation. And they're just, they just look different. And the reason they look different is because their characteristics are going in different directions. It turns out that this simple sort of trichotomy of what can happen is very special and does not generalize at all in higher dimensions. If you've ever dealt with PDs in higher dimensions, you realize that everything they taught you as an undergrad is totally worthless, right? So this is why it's so hard. That's why we have question 1. Can we detect any order of the jump? If we were only looking at second order PDs in 2 variables, like this is the entire story. There's nothing else to say, right? I mean, this is it. And question 1 is done. Question 2 and 3 are pointless because you already know how the solutions look, right? So the question is, what does this become in higher dimensions, and how do we pinpoint it? Okay, so let me sort of go back and now set this up in the general case and introduce the right notation for what's going on here. So the key word here is that these objects, these matrices are called tableaux, and their dual is called the symbol. And this is slightly different than this leading symbol of PDE that you may be thinking of. It's quite tightly related, but it's very similar, but it's a sheafy version. So
What?
Sheafy.
Sheafy. Oh, sheafified.
Yeah, it's a sheafified version of the leading order. Yeah. So it's essentially a symbol. The thing is, it's coordinate free. It doesn't depend on how you originally wrote the system, and it gives you an abstract variety as opposed to just some numbers. All right, so that's what we're going to get to, and then answer the other questions to some extent. Okay. Let's see. So, how long do we go? Yep. Yep.
Curiosity. What happens if you do not see infinity, but
You can see things.
Well, right now I'm billion.
Wait, so in terms of the solution space?
yeah, I mean you're interested in real analytic solutions.
Right.
How about holomorphic solutions to holomorphic systems? You can ask the same set of questions.
So all the theorems I know actually are about complex analytic solutions. So that's essentially, that is sort of done for. The question people spend more time thinking about is so you can certainly toss in Cauchy-Riemann equations if you want to, but that's, I guess I would personally think of that as you're just simply augmenting the original system of PDEs. So maybe your original system of PDEs is an ideal, then you tack on the extra condition of Cauchy-Riemann and everything, and then you get a new system of PDEs which you analyze again over the reals. And so that's how I personally would proceed. I don't know if there's a better way. A different direction to go is if you're saying analytic. Right? Analytic, it's fun for mathematicians, but it's not very useful for many real-world problems, right? You want smoothness, or maybe even like Lipschitz or something, right? You want like weak solutions, right? So that's a definite failure in this sort of theory, is that it almost never applies in the C infinity case. It only applies in the C omega case. There is, however, a couple very interesting papers where you can do C infinity. The theorem I'm sort of leaning towards is the Cartan-Taylor theorem, and there is there's a notion of hyperbolicity in which you can actually use the formal theory and then use it to prove that you have smooth solutions to smooth initial value problems. And this has been successful in a few cases in geometry. So there's a very good question to ask: what categories could you flip here versus C omega? The only one of the results are really good is C omega over R. Anything else, or I guess C omega over R with algebra over complexes. Anything beyond that, it sort of requires fancy techniques. It would be wonderful if there were a generalization of Newlander-Nuremberg to more general systems than it is sort of posed for, but that is beyond me. So, okay. So these are introduced some notation here. The object we're starting with is, so object to start with, is, let's take an ideal sitting in the exterior algebra over a manifold, and let's assume that it's differentially closed and generated by one forms, differentially generated by one forms, say theta 0 up to theta r. Let's say theta 0 up to theta r. And so what that means is that if it's exactly the sort of situation I wrote down in Erase with the contact system, where you're writing a system like d theta 0, d theta 1 up to d theta r, and we've already, and the original thetas sort of aren't interesting anymore. It's what their ideal looks like, and so you get some big matrix here, which I'll write pi ai, which you can say dx1. Let me say omega 1 up to omega n, and these are some. So these are some one forms which should be treated as as spanning T star of solutions. In other words, these are playing the role of dx1 up to dxn. In the geometric context I usually work in, you don't have coordinates, you just know you have a framing. So that's our independent framing, which plays the role of dx1 to dxn. So this is the structure that we have. And so the first question is, what is all the interesting content is in pi AI. So what is this thing? So what is pi AI? Okay, so this is mostly for the sake of introducing notation, but I think these are ideas which are very popular with certain people in the 50s, 60s, and 70s, and then sort of somehow have become less frequently discussed. So it's worth sort of going over them and remembering why people were using them. So as you can see in these examples, when you write on a system like this, what you end up getting is a lot of linear combinations, linear relationships among the entries of the matrix. So if you think of this as a 3x2 matrix, then you're getting, I've got that this term is 0, this term is 0, and these two terms are equal, and these two terms are equal. That's I guess 1, 2, 3, 4 linear conditions on a 6-dimensional space. And of course, the kernel there, the kernel is dimension 2, and those are the 2 independent variables, the 2 independent forms. So what is this thing representing? This is a matrix of 1 forms. The way to think about it is, let's put these omegas in a space, let's call it W. So this is dimension R. And let's put these things, let's say they span a space V, which is dimension N. So if I look at W tensor V star, when I say they span, I mean they take values in. And this is take values in. These are forms, so they take values in some vector space. In the vector space, so omega 1 up to omega n, you could think of it as being in Rn. Let's just call that thing V for the sake of brevity. So we've got, so omega is essentially RR, and V is essentially Rn, if you want to use coordinates. So I'm looking at R by n matrices, and the structure of this pi is giving me a subspace. So I've got a subspace of W tensor V star. Of course, as we know from linear algebra, when I give a subspace, it's the kernel of something. So what is the kernel of? There's some map here which is called the symbol map. And this space here is often called H1. This, by the way, is this is what's called Spencer cohomology. So at least in the history that I know, obviously everyone has their own sort of perspective on how the history of math works. In the history that I know, this perspective was sort of hinted at by Elie Cartan, but then was really developed by people like Spencer and Guillemin and Quillen in the 50s, 60s, and 70s. And then sort of picked up by, certainly Chern used this perspective a lot when he's talking about various geometric structures. And then there are many, many more recent people. But I think that's sort of the more early history of labeling things this way. And yeah, so what we're looking at here is that this pi is a form. So this is where pi AI takes values. And this is the relations among the elements. All right, so that's the way to think about this. So analysts will often really focus on the symbol, which is sort of the relations among the elements. Algebraists will maybe more often focus on the space, but of course they're dual, right? So you can work with either one you like to. In fact, it's often useful to move back and forth between them flexibly, as for diagram chasing. Okay. So I haven't yet told you anything about what this has to do with solving PDEs. So what's the goal? So the goal of solving a PDE is you find at each point in M, that's the underlying manifold we're working on here, a subspace, let's call it E, sitting inside, let's say, what do we call this point, X maybe? P, Q, let's try Q. I already used X and P over there, so. On which I matches. So that's what we mean, that's what I think we mean by solving PDEs, is we're looking for, or even better, find submanifolds N sitting inside M, and I'll think of them as being embedded submanifolds, where TQN, or let's say, if you pull back the ideal, so when I say like find a local solution to a PDE, it's like we describe the PDE as an ideal, and the solution to the PDE is the variety on which that ideal vanishes. Now, because it's a sort of it's a manifold picture, it's not, we're not working necessarily in just a polynomial ring or something, right? The variety could be the variety of sort of infinitesimal solutions at a point. So it could be little n planes, wherever n is the number of like x's we want to use. Or it could actually be the manifold, like a local submanifold on which this thing pulls back to 0. So I is playing this ideal, which is really described by pi, is providing you with an ideal. And the thing we're trying to solve the PDE, the thing we're trying to find is submanifolds, which of course by the implicit function theory can be locally described by functions in terms of your independent variables, right? So that's why this is all coming back to PDEs and local coordinates ultimately, on which the ideal vanishes. So varieties are solutions, ideals are PDE. That's the picture. So the next thing to say,
but you want a restriction on the size of the submanifold.
Oh yeah, let's say of their maximal dimension. You can certainly look for sort of sub-solutions, right? So in fact, the way this often works, you solve initial value problems. You say start at a point, and you ask, can I just find a one-dimensional solution to this this system in any equations? Can I thicken that to a two-dimensional solution, a three-dimensional solution, and keep thickening it until you get up to the desired dimension? So this is a sequence of it. You're trying to build, in the sense of this ideal, a sequence of initial value problems where you're gradually building up a local solution. Yeah, so that's exactly what we're trying to do. So actually, you could say what we're really trying to do to describe initial value problems is we're finding flags ending in E, and then sequences of submanifolds ending in N. That's maybe a better way to say it. It all depends on how much notation people want. So,
the initial value condition comes in now.
The initial value condition can be thought of as
fixing the E.
Given an E, find an N through that E. Yeah, so that's the initial value problem. So given an infinitesimal, saying, here's some family of, think of the classic thing you do in, say, calculus, right? As we look at what are they called? Flow plots of ODEs in the plane, right? No, that's not the right word. Little wind barbs. What do you call those things? What's the name I'm looking for? Anyway, so you say, I want to start here. I know it has to go in this direction. How do I fill it out to get a local graph? And that's, so given E, find N is the initial value problem.
You mean a vector field? Is that
yes. Well, no, but not just vector field, like slope fields. We call it slope fields. Right? Okay. dy dx equals a function of x.
Yeah.
So I just want to say vector fields because that somehow says you've got another variable somewhere.
Yeah.
But yeah, so just slope fields.
So in some sense, what you're asking really is you want a deformation of the E sitting inside the tangent space at that point into a submanifold. So it's a deformation problem.
Deformation.
I mean, I think of it that way. That's what I'm just asking.
So
I'm trying to deform the subspace.
So the way I can make that link is by thinking about what's that book, PDR by Gromov, called the H principle. So like, let me draw two pictures. So here's a slope field. All right, so you know, if I have this slip field, then maybe I can find a solution that looks like that. That goes, so this is the initial condition, is start at that point with this initial E, and say, can I fill it out to find something which fits all the E's locally? Whereas if something is if one of the E's is sort of pointing in the wrong direction, that might not be possible. Right? So I think of it as a thickening or an infinitesimal integration problem, but I could see it as a deformation problem. You're asking for which, if you get asked sort of how could you,
there's an obstruction to
Yeah.
deformation, does it exist fitting that? And if it does, how do you parameterize all the possible ways?
That's what I would say, yes. So what we're looking for is obstructions to yeah, that's right. So it's obstructions to finding a deformation. That's a good way to say it, yeah.
But you're sort of thinking this is, I thought you were thinking this is two different problems. You either have in the first case you want to fix the E, but in the second case you want a manifold.
Okay, so this is,
and Ray's sort of putting them together. It's just.
Yeah, maybe I wrote on the board.
I thought the E was like an initial value.
That's right. So this.
Well, that's true.
So
yeah.
up until this line is a purely algebraic problem.
Okay.
At each point, so we've got an ideal sitting over every point of a manifold. At each point, we write down its variety. It's going to be a variety in the Grassmannian of the appropriate dimension. So we're first of all algebraically finding the variety of the Grassmannian. And then we did some test from analysis to ask when can that variety of infinitesimals give you local solutions.
Yeah.
So that's the sequence of thought.
Okay.
Okay, so what I want to do next is I want to summarize. Let's see, what time do we end?
About 11:45.
Oh, okay, good. Plenty of time. This is a nice long time to discuss things. That's good. People often have like 45-minute seminars. They can't talk about anything, right? So,
It gives us lots of time to ask.
Exactly. That's the thing, right? So,
In fact, we could extend it to the afternoon.
That's right. That's right. So, I initially put this idea of like what does involutivity means about solving initial value problems in the analytic context, and I haven't sort of gotten back to that yet. But this is the first step. So, I'm going to state a little bit about how these pies can be arranged, and then state Cartan's definition of involutivity, and then come back and sort of rephrase it in a more applied context. So, okay, I'm going to redraw this. So what I want you to do now is focus the algebraic part of your mind simply on this idea here. Ignore PDEs, ignore ideals. All you've got is a vector space of matrices, and you're looking at some subspace of it. Now, of course, if you're looking at a vector space of matrices, you could ask, well, which basis have I written the matrix in? So we implicitly here, we want to understand this as a subspace of W tensor V star, or of Ham VW, if you want, you can certainly write this this way if you'd like to. Not as V and W in a certain basis, right? In fact, the whole goal of this setup is to get away from using coordinates in the first place. So you've got a GLV and a GLW to work with, and you want to sort of know what are the generic properties and generic bases of V and W of this subspace. So let me just write down what a matrix might look like. So I might have something that looks like, let's see, let me maybe use, what will I use? I'll use alphas. So let's say alpha 1, alpha 2, alpha 3, alpha 2, alpha 3. So here's an example. Here's an example of, say, if W is dimension 3, V is dimension 2. Here's a subspace of dimension 4 sitting in that 6-dimensional space. So we might ask, is this sort of the right way to write the subspace? Well, I could rewrite this. I can rearrange the bases of W, I can rearrange the bases of V, and I can also relabel the bases of A, right? It's just a basis. So I could, for example, this is sort of saying the same thing as alpha 1, alpha 2, alpha 3, alpha 4, 0, 0. Right? Because I can subtract this column from that column, that's a change of basis in V, or V star, and that kills these two terms, and this one, just relabel it as a new alpha 4. So these are really sort of the same tableau. That is the sort of thing you might want to do, right? So you can imagine doing all sorts of other things too. I guess this one I can't do much more with, but that's the idea. So the one thing that's, by doing transformations like that, and also the similar transformations in the columns, so maybe even, well, yeah, you can turn your head sideways and imagine doing the same thing on columns, so I won't on rows, so I won't say that. So what generically happens, so generically, what you have is, you can say that generically sort of the generators of A, in other words, it's where the pivots would be if you wrote if you wrote this map in, say, Gauss upper triangular form, right? So so are going to generically be in the upper left, right? Generically, they're sort of everywhere, so you may as well label them from the upper left and label the lower right based on it. So you're generically going to have, in the first column, you're going to have some number of independent generators, say alpha 1 up to alpha S1. And then there might be stuff down here. Well, let's say it depends on those. And then you might have, say, alpha S1 plus 1 up to alpha S1 plus S2. So there might be some S2 new generators here, and there's a bunch of garbage down here. And this garbage will depend on those. And so on. Until finally you've got some number, I don't know, S, what do I want to say? I'm running out of letters here. Let's say L minus 1 plus 1 up to SL, S1 plus SL. I'll say that. Okay, so we've got some total number of sort of generators, and we may as well assume that they're sort of packed in the upper left, and that everything down here is a linear combination of them. If you want to sort of make this formal, right, what am I doing? Maybe you're taking this matrix of variables, and you're writing it out, say, taking all the columns and concatenating them into make one very long vector, and then you write the equations among those, and then you do Gaussian elimination, and so you end up with the pivot ones in the right spot and all these stars in the upper right of that, and when you rearrange it, ends up that sort of the generators are here and everything else depends on them.
So you're putting a flag in.
I'm building a flag, yeah. So the point is that this shape...
In your Gaussian elimination, in the pivoting, do you do division?
Sure, if you want. I don't care. I mean, it's,
Where is it done? Where is the division taking place?
Well, so it would be in C. It would be in C infinity M if you're doing it on a manifold, or it's just the base ring R.
C infinity or C on
Either. This so far the theorem.
Yeah.
Nothing
you have to fix the category.
Yeah, fix the category first. Let's say C omega, right? So if these are bundles over M, you're working. That's your base ring, but just work over R over C. It's fine. So the point, though, is that this is the shape of this thing. So obviously, the actual relationships are going to vary as you vary W and V and sort of how you label the A's. But the shape, the number of generators in each column is generically constant, right? Certainly, there are special bases in which it's not the same. So for instance, I could do something dumb like, say, 0, 0, alpha 2, alpha 1, alpha 2, alpha 3. Right? Okay, clearly this is not sort of packed that way. But if I take, measure 1 of all the possible linear combinations I might take, it's going to be packed like this. Alpha 1, alpha 2, alpha 3, something, 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 which depends on those. And that's exactly in this form. Okay, so the thing that's constant here are the lengths of the number of independent terms in each column generically. So S1, S2. So S1 is the length of this. S2 is the length of this. S3 is the length of this up to some SL, which is the last non-zero one. So S1, S2 up to SL. Is it lower or upper semi-continuous? They can only go down on a set of measure 0, right? That's upper semi-continuous? They can fall on an algebraic set of measure 0. But that's yeah. And moreover, they have this relationship that they must not increase, because if if you had 6 generators here and only 5 here, then a generic change would move the 6 over, right? So it's clear that you're you can actually sort of pack everything in the upper left. Okay, so here's.
They don't have to be strictly decreasing.
They don't have to be strict. It can be. It could all be equal, for example. In fact, well, in this case, I guess. So in all these cases over here, S1 is equal to 2, and S2 is equal to 0. Right? 1, 2, nothing new. 1, 2, nothing new. 1, 2, nothing new. Okay. Yeah. So upper semi-continuous in bases of WV, and also A, although that doesn't really matter, of course. A very strong sense. The only case in which you get to pick exactly the right and you're fine. Here's a going back to 1904 or so. This is E-carton. That if so I have to introduce one more piece of jargon here, but if S1 plus 2S2 plus 3S3 plus NSN is equal to the dimension of a new space I'm about to introduce called A1, then the PDE represented, or any PDE represented by the space we're talking about, admits analytic solutions to analytic initial value problems. And moreover, these S's tell you exactly how to parameterize that space. Depending on, so saying that solutions exist is certainly useful, but think about the ODE case, right? There exists exactly one solution. That's pretty great. Obviously, for PDEs, you could have many, many, many solutions. The question is how many, depending on, okay, so S, so I guess R constants. R was the dimension of W. S1 analytic functions of one variable. S2 analytic functions of 2 variables. And up to the last non-zero one is I called SL. SL is SL analytic functions of L variables. In other words, what they're telling you is how many initial conditions you can set. So you can set, so basically what you need to do to choose a unique solution. So once you choose this information, your solution is unique, is what it's saying. So if you can basically jump up to the top also, because everything that went below it is to build that solution. So you can basically say, if this is, say, if L is 5, and SL is, say, 3, if there are 3 things here, then the analytic solutions you can build using, the solutions you can build using power series and the Cauchy-Kovalevsky theorem depend on, what did I say, 3 functions of 5 variables. That's what you get to pick. And once you pick that, it's unique. So it's the existence uniqueness for solutions of PDEs, but you're not picking a point. That would be this case. So if your table is empty, then you have an ODE. That's one consequence of this. Right? If all the S's are 0, then you get to choose constants. So an ODE is a PDE for which the tableau is 0. For anything more complicated, this is exactly what you get to pick. So this is called Carton's test. And this is just an algebraic, basically, trick, which is a consequence of the Cartan-Taylor theorem, which is itself simply a careful restatement without coordinates of the Cauchy-Kovalevsky. I'll appeal to the multiple transliteration of Kovalevsky to write that. So I don't, Cauchy-Kovalevsky is one of those things that some people use a lot, some people never use. So this is just simply a statement that if you have a determined system of first order PDEs given by analytic functions that you can sequentially find the coefficients of a power series that solve the system. It's the same way you say that e to the, that the power series for e to the x is what it is, because you just check that if you have a solution that's a power series, it must have the 1, 2 factorial, 3 factorial going up. So you undo that and you find the coefficients, and that's essentially what the Cauchy-Pulaski theorem does. Cartan-Taylor sort of generalizes that a little bit to a more geometric context, and then you keep track of everything you did in that theorem, and you get Cartan's test. So that's what this is.
I thought that the point of this was that they were analytic.
Yes. So this is why we need analyticity. So if you have a theorem like Cauchy-Pulaski, then you get in a different category, then you get Cartan-Taylor in that category, and you get this in that category. So these are really careful restatements of this theorem, but they're nice because if you look at this, this is that sort of question 2, right, which was, can we identify in advance if we can solve a system of PDEs? And the answer is yes. You write its tableau. If you need to, you shuffle around the basis to make sure it's generic, and you simply count. That's all you do is you count. I haven't defined the space yet, though, so I'll do that. Yeah.
I'm not sure I understand the interpretation of the SIs.
Mm-hmm.
So let's say just a 2.
Mm-hmm.
So if S2 is the number of arbitrary functions in, let's say, 1 interval, then what about, why do we need arbitrary constants, S1?
Oh, you don't need them, right. You usually jump to the last one.
Right.
Yeah. But all this information is actually telling you how to build we have the question of you're having a flag at every point.
Right.
And this is telling you how many options you had to build that flag. So the thing you ultimately care about is where you end up.
Yeah, see, in the polynomial case, because that's
Right.
differential algebra.
Right.
The last one, Sn, is, well, n is the number of arbitrary functions, number of variables in the arbitrary function.
Yes.
And that's called the differential type.
Yes.
And Sn is the differential dimension of that type.
Yes.
And this is given by a polynomial function like the Hilbert function.
Yes. In fact, these S's are the coefficients of the Hilbert polynomial.
Okay.
Yeah. So
All right.
so I wasn't sure I should use that language, right? But actually, yeah. In fact, Mark Green has a beautiful Mark Green. So he has a beautiful handwritten paper where he shows explicitly how, this is sort of always sort of known in the background, but he wrote down explicitly how that you can show that what you're really doing here is, what this theorem is actually doing is it's building the space of solutions by writing down a Hilbert, what do you call it, a long exact sequence, right?
Right.
And,
So it's almost like that if you take, I mean, let's say assuming that the system in the other case forms a prime differential ideal, and you have a generic 0, and so what you're doing is you're building the differential field like that from the ground,
exactly.
and you just go up by order.
Exactly.
Or something like
Exactly.
that.
These are the coefficients, yeah.
Yeah.
So L is the, so in fact, this is one of the things what I was going to get to,
So
is that,
where does this number 1, 2, 3 coefficient come from in this equation here?
they are the, so the,
I mean, what's the meaning of adding these numbers like that?
I mean, what are they, adding them like this? You're actually adding the codimensions. Let me define what A1 is.
Okay.
Let me define A1, and then it'll maybe become more clear. So I'll define A1 just below, because in fact it's part of a long it's part of a beautiful chain complex. Okay, so remember we're working in the exterior algebra. So the key thing we have is the exterior product, right, the wedge. So what you might ask is, well, if I have, say, a 1 form in V, what happens when I start wedging them with themselves to look at higher and higher wedge products to get through the entire algebra? So what we're going to do is we're going to say, well, look, I know that if I have anything in W tensor V star, I can tensor it with V star again and skew and be in W tensor wedge 2 V star. There's our standard skewing map. But I don't want to use all of this space. So this is certainly onto, right? Normally we have this picture. And and the kernel is, I guess, sim2, right? But that's not what we want to look at, because we're not looking at all of this, we're looking at only A. So we take A and we put it here. So anything in A embeds into here, tack on a V star and wedge. And in fact, let me call this map sigma, and this is delta sub sigma, because it somehow is encoding some of the information about sigma in that, because it's using the kernel to move forward. This has itself a kernel, which is called A1. And this, of course, has a co-kernel, which is called H2. And that's the second Spencer cohomology. What's the third Spencer cohomology?
Is it still going to W here?
Yes.
Okay. Oh, so it's no longer surjective. Okay.
That's right. It's no longer injective nor surjective. Yeah, so. And so we keep track of both pieces. And you can see what's going to happen. So they might call this delta 1 or something, but I'll just leave it as delta. We get a whole sequence of these A's. You just keep going. So this is like the, in fact, I should push this over by one block on this to make this diagram pretty, right? So in fact, well, let me do that, because then I can draw a nice arrow. It's just too...
Stop shading.
Okay. That's a nice picture. One thing that this was actually Daniel Cohen's thesis, his PhD thesis back in, what was it? Like 62 or 63 or something like that. He proved that this sequence is, the sequence which is induced here is exact. And that actually has lots of important consequences for knowing that if you sort of formally solve a PDE, you can actually solve it. So is this sort of a, yeah, anyway, that's, I'm going on too many tangents. So,
How do you get those maps on the right?
let me erase them. I don't want to go there. So there's a mistake to drop them. So what we do have though is we have this, and then we have this space A1. So what we're doing here is the way you think about this in terms of the PD is what you want to do is you want to make sure that if you have, say, you want not only the second derivatives to commute, but the third derivatives to commute, and the fourth derivatives to commute, and the fifth derivatives to commute, right? So W tensor V star is where all the where the first new derivatives appeared, and they live in some subspace. And then we make sure if we wedge with the independent variables again, right? So saying that, so you want to lie in A, and then you want to lie in the kernel, and this kernel, and this kernel, and this kernel. And that guarantees that the image of the PD you've written down always. Right, this means being in the kernel of this map means that you only have the symmetric part. You only have the symmetric variables. So these are the important spaces. So it's the tableau and its prolongations.
So it's kind of a prolongation, isn't it?
It's the word. So this is the prolongation of A. And so this is the algebraic context in which this thing we always do, which is we say, okay, I want to study this PDE. By the way, this of course implies that U221 is equal to U111 and so on.
Exactly.
So these three indices are coming from, I guess, well, the way I've written that, I guess from here.
By the way, the whole theory is for arbitrary PDE, not linear, right?
Correct. One thing that's sort of amazing is that it looks like this has to be linear, a first order PDE, a quasi-linear PDE, because you're writing like dy's and dx's.
Right.
But that's
so you're linearizing it, basically.
Well,
in some sense.
I am very
taking the linear part of it.
Let me put it this way. Okay, so if you're doing differential geometry on the sphere, and you decide to work on R2 instead by looking at the tangent space of the North Pole, I think that's linearization.
Mm-hmm.
What we're actually doing here is working on the entire tangent bundle simultaneously.
Mm-hmm.
So if you linearize at every point simultaneously, that's not really linearization, that's bundleification or something.
But more than that, you're only doing this one order at a time, and the obstruction is linear.
Yeah.
Yes, yes, yes. So that's true. So each time, so the obstructions, the obstructions live here,
Right.
and the sort of solutions live here.